Hi, I'm Bennett Alterman, and today we're going to examine the motion of an oscillating arc-swinging spring mass system. So the objective of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. Here we've included the mass, the spring, and the earth all in our system. Our mass weighs 0.402 kilograms, and our spring constant found from the 1D lecture video is 6.83 newtons per meter. Our time step is also given to be 1/210 or 0.0048 seconds. The only forces and interactions at play in this particular model are the spring force and the gravitational force. Our results are that our delta K is 7.96 times e to the negative fifth joules, our U gravitational is negative 0.0014 joules, and our U spring is 0.0013 joules. Our delta E is the addition of these three, giving us negative 1.69 times e to the negative fifth joules. Here in our free body diagram, we see that the positive x-axis points to the right and the positive y-axis points up. You'll notice that the spring, the earth, and the mass are all included in our system. Some important equations we'll need to know for this lab are as follows. The change in total energy, or delta E, is equal to the change in kinetic energy plus the change in gravitational potential energy and the change in spring potential energy. Since all three of these objects are included in our mass, we know that delta E, or the total change in energy between the system and the surroundings, will be 0. To calculate the spring force, we multiply the negative K, which is the spring constant, times S, which is our compression or stretching length, times L hat, or the direction of the stretch. Kinetic energy is calculated by multiplying 1/2 times the mass and velocity squared. Gravitational potential energy is found by multiplying mass times gravity times the height. And the potential spring energy is found by multiplying 1/2 times the spring constant K times, again, the relaxed or stretched or compressed length of S squared. We're also going to be looking at the period, which is the length from one crest to one crest, or one trough to one trough in an oscillation. This is found by multiplying 2 pi times the square root of mass over the spring constant K. Here in our tracker video, we can see that the origin is placed at the fixation point of the spring. And as Dr. Greco releases the mass, it oscillates in both a x and y direction. Here we see data obtained from tracker. You'll notice opposite oscillations for the x data and for the y data. Moving on to the code changes, we've inserted the initial ball's mass as well as the initial position vector. We've also inserted the spring constant K to be 6.83 and the L naught to be 0.123. Again, these two values are calculated from the one-dimensional lecture video. We've also updated the equations for kinetic, gravitational potential, and spring potential energy. Here we've updated the time as well as our initial conditions for K, U, G, and US. And we've also input F net to be the force of the spring plus the force of gravity. And towards the bottom you'll see calculating energy changes. To find delta K, use K minus K initial, and the same is done for delta UG and delta US. As we run the code, we're able to see that the blue and red dot, which represent the model data and the tracker data, follow almost identical paths, but very slightly. This will compose a graph you'll see on the right that we'll talk about in one moment. Here, the blue arrow indicates the direction and magnitude of the spring force, while the black arrow indicates the direction and magnitude of gravitational force. So looking at this graph, in red you'll see the change in potential spring energy, in green you'll see the change in gravitational potential energy, the blue indicates kinetic energy changes, while the yellow indicates total energy changes. You'll notice that because the gravitational and spring potential energies are opposing, and the kinetic energy again makes up for this slight difference, that our total energy change remains around 0 for the almost entire time period that we observed in this tracker video. And our results give us a delta K of 7.96 times e to the negative fifth joules, a UG of negative 0.0014 joules, a U spring of 0.0013 joules, and a total energy change, or delta E, of negative 1.69 times e to the negative fifth joules. So what does it mean? Do we satisfy the energy principle? The answer is yes. because we previously stated that changes in total energy are equal to changes in kinetic plus changes in gravitational potential plus changes in spring potential, that when we add these together, we observe an energy change of 0 because all three objects are included in our system and there is no exchange of energy from the environment to the system or vice versa. Here we're able to estimate the period from our tracker data by observing the length between one crest and one crest in the x direction and the y direction. This is different from the data we observed from the lecture video because the spring actually pulls in the x and y direction, and this causes the mass to move through space in a different distribution than it would under ideal conditions, as you would see in a computational model. So this accounts for the variation we see in period from the x and y direction. Thanks.